Welcome. Today we're going to talk about one of my favorite integrals to compute, and that is the improper integral, so from 1 to infinity of 1 over 1 plus x cubed dx. This is a very interesting problem. It uses a lot of the skills, not just from Calculus 2, but also from our first semester calculus. There's a lot of places to make mistakes, but if we're thinking ahead, there's also a lot of places for us to know that we are going to make mistakes, and we can find out the answers to those very quickly. So anytime I look at an improper integral, the very first thing I ask myself is, does it converge? Knowing that is going to be the most important thing, because if I know it converges and I make some algebra mistakes, so I get a non-convergent integral, I can already tell immediately that I've gone wrong. So we definitely always want to guess if it converges or not. Luckily in this case, it's pretty easy for us to tell. So let's first instead look at just the integral of 1 over x cubed. By the p-test for integrals, since 3 is bigger than 1, I know that this integral converges. And I now know that since 1 over 1 plus x cubed is less than 1 over x cubed, my original integral, is going to be smaller than this convergent integral. And since the integral from 1 to infinity of 1 over 1 plus x cubed dx is less than the convergent integral from 1 to infinity of 1 over x cubed dx, I get to say that our original integral converges by the comparison test. So let's keep that off to the side. Okay, we're going to tuck that information away. It's important for us to remember for later. Alright, we know it converges, so it's worth our time to compute. If it didn't converge, that would save us about 10 minutes, but since it does converge, we're going to have to go ahead and compute it now. There's no obvious u sub that I can see. There's no obvious trig sub either, since I have a cubic. But it is a rational function, which means I'm going to try to use partial fractions. Now for us to do partial fractions, we're going to have to factor. Luckily 1 plus x cubed is a difference of cubes, which has a nice formula. So the difference of cubes always decomposes in the same way. It's important to note that that second quadratic term is irreducible. So a difference of cubes, I get a linear term times an irreducible quadratic. Since that second term is irreducible, that gives me the following partial fraction decomposition. So I'm going to have 1 over 1 plus x cubed is going to be some constant over 1 plus x, plus some linear term over my irreducible quadratic. So if I compare the quadratic terms, I get a plus b equals 0. If I compare the linear terms, I get negative a plus b plus c equals 0. And finally, comparing the constants, I'm going to get a plus c equals 1. Now, I don't expect any of you to do this in your head. This might be a nice time to pause the video and see if you can go ahead and get the exact same system of equations. Maybe also take the time to see if you can reduce this system and get the constants of our partial fraction decomposition. So we solve this system. We're going to get a equals 1/3, b equals negative 1/3, and c equals 2/3 by solving that system. So let's plug them back in. So I have the following decomposition: 1/3 over 1 plus x plus negative 1/3 x plus 2/3 all over x squared minus x plus 1. I'm going to take a 1/3 out in front just to clean everything up. And then also that irreducible quadratic, I want to be able to integrate this using either u substitution or the rules for arctan, so the antiderivative of 1 over 1 plus x squared. To do this, anytime I have an irreducible quadratic, I want it to be of the form x squared plus a squared, which means I've got to complete the square. So x squared minus x plus 1, I'm going to complete the square and turn it into x minus 1/2 squared plus 3/4. Okay, that's the first step. Because this allows me to now decompose that second fraction. And now I have 1 over 1 plus x minus, so the minus sign gets brought down out in front, highlighted in red. So this becomes x minus 1/2 over our completed square, x minus 1/2 squared plus 3/4, plus 3/2 over that same fraction. Again, I want to do this because this first term I'm going to use my natural log rules. The second term I'm going to try to solve using u sub. The third term I want to use arctan. Both the u sub and the arctan are going to require me to complete the square. Since I have an x minus 1/2 squared, I want that same exact thing in the numerator to help me when I use u sub. Alright, so let's carry this out. I'll get my original integral, my improper integral. I'm going to change it into a limit of a definite integral. And I'm going to integrate term by term. Okay, with these definite integrals, I can integrate term by term. Each one individually I know how to handle. So let's look at those integrals. And again, the first integral, I'm going to just use my table of antiderivatives to get the natural log. The second integral, I'm going to use u substitution with u equals x minus 1/2. And the third integral, I'm going to use the antiderivative of arctan, or my arctan rule for the antiderivative of 1 over x squared plus a squared. This gives me this following mess. So now my original integral is going to be 1/3 times the limit as t approaches infinity of the natural log of 1 plus t minus the natural log of 2 minus 1/2 times the natural log of t squared minus t plus 1 minus the natural log of 1 plus the square root of 3 times arctan of 2 over root 3 times t minus 1/2 minus the arctan of 1 over root 3. Let's start computing some limits. Well, if I look at this first term, the natural log function is increasing and unbounded. So that means that very first term goes off to infinity as t goes off to infinity. Does that mean I'm done? One piece of my sum goes off to infinity. Does the whole thing diverge? Well, clearly not, because again, from the very beginning of the problem, I know that my integral is convergent. So just because that first term goes off to infinity, I can't state that the entire integral is divergent now. Well, what's going on? So yes, the first term might in fact have a limit of infinity, but the natural log of t squared minus t plus 1 also goes off to infinity. And as we know from Calc 1, infinity minus infinity is an indeterminate form. So it's not just enough to say that one term goes off to infinity so the whole integral is divergent. I've got to be very careful about my indeterminate forms, and in this case, I have an infinity minus infinity. So let's do some algebra. Remember that coefficients in front of the natural log become powers. So that 1/2 natural log of t squared minus t plus 1 becomes the natural log of the square root of t squared minus t plus 1. And subtraction in the logarithms becomes division inside the logarithm. So the natural log of 1 plus t minus 1/2 of the natural log of t squared minus t plus 1 becomes the natural log of 1 plus t over the square root of t squared minus t plus 1. And that is a limit that we know how to deal with very easily. So now my indeterminate form is infinity over infinity, which you can deal with very simply. Let's look at it. Natural log is continuous on its domain, so I can pull the limit inside and compare just the limit of that algebraic expression. And 1 plus t divided by the square root of t squared minus t plus 1 is going to go to 1. The natural log of 1 is 0. So now when I compute my limit, I'm going to get 1/3 of 0 minus the natural log of 2 plus the square root of 3 times pi over 2 minus pi over 6. The limit as t approaches infinity of arctan of t is going to be pi over 2. So arctan is an increasing function, but it's bounded by pi over 2. It heads towards pi over 2. And then the arctan of 1 over root 3 is pi over 6. So we simplify this out, and I get pi over 3 root 3 minus the natural log of 2 over 3. There we go. That's a number. That's a convergent number. And I can conclude that my integral from 1 to infinity of 1 over 1 plus x cubed dx is equal to pi over 3 root 3 minus natural log of 2 over 3. But we're not done. Let's stop and think about this just a little tiny bit. So this is going to be around 1/3, a little bit bigger than 1/3, which is certainly less than pi over 4, which is closer to 3/4. Well, why does that matter? Because pi over 4, I know, is the improper integral from 1 to infinity of 1 over 1 plus x squared. Because that's the limit as t approaches infinity of arctan of t. That's pi over 4. Which then makes sense because I know that the integral from 1 to infinity of 1 over 1 plus x cubed has to be smaller than the integral from 1 over 1 to infinity of dx over 1 plus x squared, because the integrands are smaller. So my numeral answer, it makes sense that I got a number because I know my integral converges by the comparison test, and the size of my answer makes sense because I've also been able to bound it by a convergent integral that I know the value of. So all of our work, we caught some easy mistakes, and we know our answer makes sense. And so there we go. We have used all of our tools to not only show that the integral from 1 to infinity of 1 over 1 plus x cubed is convergent, but we were able to find the exact value of pi over 3 root 3 minus the natural log of 2 over 3. Now, if you try this integral on your own, notice this has been a 12-minute video where I've been walking through all of the steps. And I skipped a lot of them. When I did this by hand, it took me about 9 pages of work and about 20 minutes of writing, and I knew exactly what I was doing. So this is definitely one of our more challenging integrals, but I thought it was interesting just because of the raw number of skills that you have to learn. Hopefully you learn something from it. Most importantly, it's always helpful to guess and to use our comparison test or whatever tools we have available to see if the integral converges first. Once we know the integral converges, that's going to help us figure out and catch a lot of our mistakes. All right, thanks.